right. So to finish talking about waves and sound, we just finished talking about what's required for transmission of sound waves, which is some sort of medium, solid, liquid, or gas. There is something else that's unique about light, which we're going to talk about in a few chapters, in sound, which is that there are boundary effects. So a boundary effect is going to be where you have two different types of medium or two different types of environments, and sound is having to travel from one into the other. So three things can happen. Reflection, which is the wave bouncing off of a boundary, just like something reflecting off of something else. Refraction, which is really a bending, but it's where the direction of the wave front will change or bend. And then absorption is where the wave energy is dissipated, so it's going to be absorbed by the material. And then the types of boundaries we have are different types of materials, solid, liquid, gas, different regions of the same material but under different conditions like temperature and pressure. We see this a lot on cool and warm days where planes are flying above. Whether you hear the sound on the ground or you don't is because of the differences in the temperature of the area in which the plane is traveling over. So let's look at them a little bit more specifically. So reflection. Reflection is where wave rebounds off the surface. Reverberation is going to be the sound enhancement from mixing of original and reflected waves. So reflection is just going to be me talking in a room and the sound bouncing off the walls like you see here in this image. Depending on how quickly it reflects, sometimes you can perceive what's called an echo. Reverberation, on the other hand, is going to be why it sounds like you sing really well when you're in the shower, because all of the sound is bouncing off of you so quickly and it's enhancing because of the walls of the shower, enhancing and building up to make this really big, wonderful sound that doesn't really exist when you're not in the shower. So that's reverberation. An echo is going to be a reflection where there's a really specific time requirement. It's if the human ear can distinguish it, and that because you're talking, there's a delay in the original sound and the reflected sound. And it has to be greater than 0.1 seconds. So that should tell you how fine-tuned the human ear is, because that's not very long. 0.1 seconds is a very short period of time. And so that's where you hear things like, hello, 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 hello. You know, you see people holler out. In Lion King, that's an example where he's hollering down into the gully for help. Hello, is anybody there? And you can hear his voice echoing back. That's a great example of an echo. Now, we also use echoes in sonar and ultrasonic imaging. So down here, like how they map the bottom of the ocean as best they can is using sonar technology, which was first developed in World War II, I think, so that they could detect other submarines that were underground. But the sound that goes down is then bounced back up. And they know if the sound returns quicker, then there's not as much distance between the source of the sound and the ground, versus the sound takes a really long time to reflect back. So that's how the sonar imaging works. Now, refraction, on the other hand, is that bending. So the bending of wave fronts because it's encountered a boundary. So sometimes it's between two different media, solid, liquid, gas. Other times it's because there's a different set of physical circumstances, remember temperature and pressure, but the medium is both solid or both liquid or both gas. So the example here is the temperature gradient in the air, which we haven't gotten to earth science yet, but you might know that as you go up in the atmosphere, the temperature is going to change. It becomes cooler, which you might know if you've ever been into the mountains, it's colder there, and that's not because it's just colder there, it's because those mountains are higher up in the atmosphere where it's colder. But there's also going to be a temperature difference sometimes that makes the cold air, maybe a cold front has blown through, the colder air is on the ground and higher up it's warmer. So what happens if we have a plane fly over and say that it's cold down on the ground where you are, but it's actually warmer up high where the plane is, the sound is going to bend down towards the cold air because it's going to travel slower and you're going to hear the plane fly by. When the opposite's true, the warm air is down on the ground and the colder air is up high where the plane is, the sound is going to bend up and you won't hear the sound of the plane going by as much because most of the sound is bending up into the upper part of the atmosphere and not bending down towards you where you are on the ground. Now, interference, we're going to have two different types of interference. The first is going to be constructive interference. And this is where you're going to have two or more waves combine. So the waves that are combining here are the red and the blue ones. And you can see here that when the red and blue add together, they're overlapping at the same time. If they're both worth the value of 1, well, 1 plus 1 is 2. -1 plus -1 is -2. So in constructive interference, the waves are going to overlap each other and they're going to add up, kind of like reverberation. They're going to build up and enhance the overall wave. What must happen with constructive interference is the peaks must be aligned and the troughs must be aligned. So peaks are aligned, troughs are aligned. Peaks and troughs, okay, which enhances the total wave. Destructive interference is the opposite. This is where the wave is not going to be built up because you're going to have the peak and the trough and the peak lining up, and that's going to cancel the wave out. So if I want to draw it to look like the last one, say that this is my first wave, okay, and then my second wave is like this. Well, now, if this is 1 and this is -1, 1 minus 1 becomes 0. So what happens is the overlapping of the peaks to the troughs is going to lead to a diminished wave and sometimes a full cancellation. So you can see right here, there's no wave to be even detected. Now, we're not going to worry about beats. Okay? We're going to only worry about constructive and destructive interference. What the wave would look like, what happens to the waves once we have constructive and once we have destructive interference. Okay? Destructive interference is kind of like noise canceling. If you've had noise canceling headphones or worked in something that's soundproof, it's going to be an example of destructive interference. So loudness. We're going to have two different types of systems that can be used to describe the loudness of a sound. And loudness is not the same as what we would call the pitch of a sound. Pitch has something to do with frequency, which if we remember back, it's going to be whether the wave looks like this, which is high frequency, or like this, which is low frequency. So loudness, on the other hand, is a subjective interpretation that varies from person to person. It's related to the energy of the object, the condition of the air that the sound is traveling through, and the distance between you and the vibrating source. So the further you get from a sound, we know the sound is going to become more quiet or less loud. When we double the amplitude of a source, so we increase the peaks and the troughs, the intensity of the resulting sound wave will be increased, but the sound will not be perceived as 4 times as loud. So intensity and amplitude are also not related to sound. Intensity and amplitude are objective, measurable things. Loudness is considered to be subjective because it differs from person to person. Your detectors are your ears, and that's not something we can quantify. So the two different types of systems we're going to use are the decibels and intensity. So the decibel scale is going to be a logarithmic, so it's based on factors of 10. And so you can see here that it's going to go from 10 to 120, 0 to 120, which is barely perceived, all the way up to jet plane, which is very loud. And like it says here, the response is discomfort, so you would close your ears most likely. The intensity watt meter is going to go from a very, very tiny number to a value of 1. Okay, and it's going to have the same examples and the same response. And so you can see they're kind of different scales, but the intensity scale is going to have a factor in it that the decibel scale doesn't have, which is the factor of meters per second. All right, resonance. So resonance is going to be the excitation of the natural frequency or resonant frequency by matching the external driving frequency. So one of the best examples here is going to be striking a tuning fork with a hammer. Okay, so even though the tuning fork, and we know that's going to produce sound. However, even when we don't hit the tuning fork, it still has a vibration associated with it. And it's kind of hard to see the little blue lines right here, but they're here. So when we hit it with a hammer, there are just more. Okay, so every single object, no matter what, is going to have a natural frequency, okay, inherent. And the way we see this in our everyday life is that when you have like a really loud explosion, when I live in Waco, when the West fertilizer plant explosion happened, the fertilizer plant exploded, but then people's houses for miles were decimated. The ceilings fell in, the windows broke, and that's because of the waves, the resonance being matched and breaking it. Some other examples are whenever you have a singer, the classic example of a singer breaking a glass because they've matched the natural frequency of the object with the pitch of their voice. When you're driving down the street, if something's rattling in your car and you can't figure out what's rattling and you'll finally find it and you put your hand on it and stop, well, the rattling was matching the natural frequency of the object to your movement on the road. So we don't attribute those things to resonance, but that is why we see those things in our everyday life. So sources of sound, anything that's vibrating, and we just said that everything has a natural vibration, is going to be our sources of sound. Now we have two different types of sound. There's the sound we like, and then there's the sound we don't like. So irregular or chaotic vibrations produce noise. So when someone's drilling something, that probably doesn't sound like beautiful music to you. It probably sounds chaotic and painful. It's because it's irregular, chaotic vibrations. And it's also very loud. When we have regular, controlled vibrations, this can produce music. It's the difference between the band warming up at the very beginning and everybody playing whatever they want versus playing the orchestrated pieces of music. Now, the warm-up still may sound pretty, but it doesn't sound as nice as the music that's been orchestrated. And all sound is a combination of pure frequencies. Those ones we talked about, that everything has a natural frequency associated with it. Now there's one more thing we're going to talk about, which is moving sources, because everything we kind of talked about so far is treating it as a stationary source. But when we have a moving object, something different occurs, which is called the Doppler effect. It has nothing to do with weather, but it's the Doppler effect. So if we have a stationary sound, that's what's up here. All the waves are going to travel out in regular patterns to the left, to the right, to the up, to the down, perceived by ears. It's going to sound the same no matter where you are around the object. When we have motion of the source of sound, that regularity is gone. So when we have an object that's moving, so this object's moving from left to right, we see that the waves here are further apart than the waves that are in the direction of the motion. So all of the sound, if we had another ear up here and another ear down here, they might be the same on up and down, but they're not going to match what the people on the left and the right hear. So this is why we have differences in perceived sound when the object is moving. So when the object is approaching, we're going to have a higher frequency. Remember, these are the waves that are closer together. And when the object is moving away, that's going to be lower frequency. So the wave is a little bit not as repeated. Now, the most common example that I know of the Doppler effect is an ambulance or a fire engine or a police car, something with a siren coming at you. So as it's coming towards you, you hear wee, 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 wee. And then after it passes you, the very moment, the sound changes to woo, 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 woo. And that's not because the siren's pointing out one way and not the other way. It's because the sound was coming towards you and your ears were hitting it at a higher frequency than when it's going away from you. So anything that's a moving object is going to have the Doppler effect, but an ambulance, fire engine, cop car, things with sirens are going to be similar to this type of observation. This would be more on the top part, the stationary source, like a tornado siren. No matter where you are around the tornado siren, it's going to sound the same because the source of siren is not moving. All right, so this ends all of chapter 5, which was our discussion about waves, motion, and sound.